This video introduces the number e, especially in context with interest on loans and borrowing money. So here's something we discussed in a previous video. If you borrow $A at an interest rate of R% annually, and that is compounded n times a year for t years, then you owe, at the end of this time period, an amount equal to A times 1 plus R over N to the NT power. So as a somewhat silly example, but there's a point to this example, if you borrow $1 at 100% interest rate, compounded n times a year, for 1 year, you owe an amount equal to 1. So I'm taking A, R, and T to equal 1, and N to just equal N. So you'll owe 1 plus 1 over N to the N power. And this is a quantity that's actually pretty interesting. So I want to make a table of values of this form. So I have N, and I'm going to make a table of values 1 plus 1 over N to the N power. So if I plug in N equals 1, I get 1 plus 1 to the 1 power. So 1 plus 1 is 2, if you don't know. 2, if I plug in N equals 2, I get 2.25. If I plug in N equals 12, let's say we are using the interest idea here, so 12 would be compounded 12 times a year, meaning once a month, then I get 2.613, and so on. This number keeps going on. If I compound it 365 times a year, so once a day, I will get 2.714. And if I actually compound the interest 1,000,000 times, so let's say 10 to the 6th power, that's 1,000,000 times a year, then this number will be close to 2.7182, etc. What I'm trying to illustrate here is that if you increase this N value, you don't necessarily increase this quantity by a large amount. In fact, these numbers, 2, 2.25, 2.6, 2.7, 2.7, are approaching a single value. If I even increase this to 10 to the 10 to the 10 to the 10 power, that's a ginormous number you can't even really understand, you'll still get a number that's really close to 2.7182 and so on. So the number that this is approaching is a very special number. In fact, it's my personal favorite number in all of mathematics. As a professional mathematician, I've seen a whole bunch of numbers. I've seen 1, 2, 3. I've seen a whole bunch. But E is my absolute favorite. This approaches the number E, and E is approximately 2.718281828459045 4, 5, and this number keeps going on without a pattern in its decimal approximation. It's similar to pi in that these digits don't have any sort of pattern that you can follow. This is a very, very special magic number in mathematics. It appears all over the place, and if you continue on to take calculus and even continue past that, you'll see the number e over and over again. It's just all over the place. If you'd like to remember the decimal approximation of the number e like I did by just writing it down quickly, then you may be able to leverage your vast knowledge of the 7th President of the United States, Andrew Jackson. If you know Andrew Jackson, then you know that he was the 7th President of the United States. So 7th President is Andrew Jackson. He was elected president in 1828. So this is the year he became president. He served for 2 terms, so 1828 is listed twice. And what was Andrew Jackson's favorite triangle? Well, it's everybody's favorite triangle, a 45, 90, 45 triangle. So this is his favorite triangle. The triangle with angles 45, 90 degrees, and 45. So anyway, that's how I personally remember the decimal approximation of the number e. The natural exponential function so we've seen exponential functions, but the natural exponential function, the one that's kind of the best, is the function f of x, which is e to the x power. We've seen graphs of exponential functions before, so I'll just remind you very briefly of what this graph looks like. It starts off at a very number close to 0. So if you're a negative number, e to the negative exponent is very small. It crosses through the graph at x equals 0, at y equals 1. And then grows very rapidly. So this is the graph of the function e to the x, probably the most important function in all of mathematics. I can't get to why it's such a critical function, but as you continue on in mathematics, you'll just see it more and more and more. One reason, for example, in the context of compounding interest, is the following. So if interest is compounded continuously, so instead of compounding it once a month or once a day or even a billion times a nanosecond, you never stop compounding interest. The amount that you would owe in this situation is a times e to the RT. AE to the RT. So this is the amount of interest you would owe if you borrowed $A at a rate of R% for T years. Why is that? Well, this is because if you write this formula, A times 1 plus R over N to the NT power, you can write it down a little bit differently. You can use properties of exponents to say that this is 1 plus R over N to the N over R power, and then you can multiply all that times RT, so the R's cancel here. The only thing I did from this step to this step here was I replaced the N with N over R and multiplied by R, so it's kind of a sneaky trick. And then this term in here becomes the E, because that's kind of what you're doing with this calculation that you can see here. Let's finish this video with a final example of using this formula for compound interest compounded continuously. So if you borrow or let's say instead of borrowing, let's say you're an investor now. let's say you invest $5,000 at 10% interest, compounded continuously for 40 years. This is actually a realistic scenario for many people in this class, possibly because let's suppose somehow you were able to save $5,000 in a year. That's about saving $100 a week, and you put it in an index fund in the stock market. The stock market historically has grown at a rate of about 10% annually. So let's say you do that, and if you're 25 years old when you put in $5,000 and you take it out when you're 65, 40 years later, how much money would you have? Well, this would be 5,000 e to the 10%, so 0.1 times 40. So e is this number, 2.718. If you plug that into your calculator, you will find approximately $272,991. So this is a testament to how quickly exponential functions grow. They grow exceedingly rapidly. Almost every human being underestimates how quickly they actually grow. So there was our first introduction to the number e. Okay, wonderful.